Welcome to the Deep Dive. Today, we're launching into the definitive engineering challenge facing the next era of transportation, advanced air mobility, or AAM.
And we're not just looking at concepts, we're digging into the blueprint.
A highly technical blueprint for how these aircraft not only get off the ground, but prove they are safe and, well, commercially viable for the long haul.
That blueprint is really encapsulated in the P13 series Parallel Hybrid Propulsion Engineering Specification. This document, it's the absolute state-of-the-art in aviation electrification.
And it has to be, right?
It does. This system is the bridge, the strategic pivot that allows AM to escape the limitations of current physics.
And that limitation is a massive, just unavoidable physics problem that has stalled the industry. Right now, every pure electric eVTOL is running headfirst into what the industry bluntly calls the Valley of Despair.
The Valley of Despair. It's created by the constraints of lithium-ion battery technology. Despite decades of massive investment, the commercial energy density remains stubbornly stuck.
Where are we at? About 200?
Somewhere in the 250 to 280 watt-hours per kilogram range. And that physics wall, it means the pure electric dream is only viable for very short intracity hops, maybe 50 to 100 kilometers at best.
Which is fine for, an air taxi in Manhattan, but it completely kills the commercial model for the lucrative regional routes.
The real city-to-city trips.
Exactly. The 150 to 400 kilometer range.
Yeah.
That is the volume business that defines true air mobility. So the strategic resolution, as defined by the architects of this system, is this P13 hybrid architecture.
It is the essential bridge technology, but, and this is critical, there's a pivot baked into this design philosophy.
Okay.
You cannot simply bolt a combustion engine onto an electric propulsion system, not using the fast and loose trial and error development methods you see in the auto sector.
This is aerospace.
This is aerospace. This pivot demands complete documented aerospace-grade rigor. We're following system engineering principles like top-down design and, MCE structure.
MCs being mutually exclusive, collectively exhaustive.
Precisely. Because failure here isn't a recall. It means catastrophic loss of the aircraft and, frankly, the end of the industry.
So our mission today is to take that top-down view of this highly complex engineering spec. We're going to unpack the architecture, the development process, and the testing. The goal is to give you, the listener, a shortcut to understanding how this system is defined, how it's built, and how it's ultimately proven safe.
And the stakes couldn't be higher. This system is designed to meet the most stringent safety goal, the ESA SC VTOL Enhanced Category Safety Target.
It shows.
It requires proving a catastrophic failure probability of less than 10 to the minus 9 per flight hour.
Wow.
That is the safety reliability threshold required of a large commercial airliner. Think a Boeing 787 or an Airbus A350.
Let's put that figure in perspective. 10 to the minus 9. That means one failure in a billion flight hours.
Yeah.
That's like proving that in the entire lifetime of a global eVTOL fleet, over decades of constant operation, a fatal propulsion failure will basically never happen.
It's as close to never as engineering can get.
So if you want the technical foundation for understanding this next phase of air travel, this deep dive provides the necessary knowledge across the three interdependent pillars of eVTOL success: architecture design, energy and propulsion engineering, and the stringent certification ecology that governs it all. Okay, let's unpack this architecture first. It's a series parallel hybrid.
Right.
So that means it uses two distinct power paths that have to operate together seamlessly, but crucially, they also have to fail independently.
That's the key, heterogeneous redundancy. You're mixing fuel and electricity.
So what are the 5 core physical nodes that define this mechanical and electrical duality?
The architecture is built around 5 specific physical nodes that provide fault tolerance, multi-mode flexibility, and, well, the complexity that makes it so challenging to certify.
Let's start with node 1.
The anchor of the long-range capability is the first node, the ICE, or thermal engine. This uses high-energy density liquid fuel avgas, or jet fuel, for sustained energy.
This is what gets you past that 100-kilometer battery wall.
This is the reason the P13 can fly 300 kilometers when a pure electric vehicle is grounded. It solves the range anxiety problem.
But it introduces a whole host of mechanical complexity. Vibration, for example. Things pure electric avoids. So what's coupled to that ICE?
That's the second node, the P1 ISG, the high-voltage integrated starter generator. It's coupled directly to the ICE crankshaft.
And I'm guessing it's more than just a starter.
Oh, much more. It's an active subsystem with 3 highly critical roles that are constantly being executed.
Okay, the first 2 seem obvious. A reliable, rapid start for the engine, even in flight. and high-efficiency power generation when you're in series mode. But what's that crucial third role?
The third role is the real engineering masterstroke, and it's the hidden key to reliability: active torque damping and assistance.
Okay, what does that mean?
A combustion engine, by its very nature, produces enormous torsional vibrations. Torque pulses every single time a cylinder fires. If you leave those unchecked, those high-frequency impact loads would dramatically shorten the lifespan of everything.
The bearings, the clutch.
The bearings, the P3 motor, and critically, the K0 clutch mechanism. So the P1 motor actively outputs or absorbs tiny bits of torque microcorrections to effectively smooth out those vibrations.
It's like noise-canceling headphones for torque.
That's a perfect analogy. This torque fill dramatically reduces mechanical fatigue in the entire driveline. It's an active stabilizer running in the background, a core function for durability and long-term safety.
Wait, so the P1 isn't just making electricity, it's actively protecting the engine from vibrating itself apart.
Exactly.
That's a huge hidden safety function. And it immediately highlights why the control unit has to be so sophisticated.
Absolutely. The P1 is the definition of a highly integrated mechatronic component. Now, to your question about where those two energy paths can physically meet and separate, that happens at the third node,
Which is?
the K0 decoupling clutch.
This sounds like the linchpin, the true heart of the architecture.
It is. It is the single element that dictates the system's operational mode and provides essential physical safety. When the K0 clutch is open, the ICE and P1 can run independently as a range extender, or they can be shut down completely.
Leaving you in pure electric flight.
Right. And when it's closed, it lets the ICE's mechanical torque drive the propeller directly for high-efficiency cruise. But the safety part is crucial. The K0 clutch must be designed as fail-safe open.
Meaning if anything goes wrong, it defaults to opening up.
Yes. If the ICE suffers a catastrophic failure, say it seizes up, the K0 clutch must be guaranteed to open, physically isolating that jammed engine from the propeller shaft. This ensures the P3 motor can still drive the propeller electrically and fly the aircraft home.
A mechanical fuse, basically. So moving past that critical isolation point, we find the workhorse that provides the actual thrust.
That's the fourth node, the P3 propulsion motor. It sits downstream of the K0 clutch and directly drives the propeller. The P3 is the system's primary mover. It provides 100% of the thrust during quiet VTOL and delivers the peak torque, the boost, when you need max performance.
And linking all these dynamic components is the high-voltage electrical nervous system, the fifth node.
That is the HVDC bus. This 800-volt backbone, which typically runs between 600 and 900 volts, links the battery storage system, the P1 inverter, and the P3 inverter. It's what enables the sophisticated energy management strategy, or EMS.
The brain deciding where the power comes from and where it goes.
Exactly.
So we have the physical components. Now let's apply that MEC principle to the logical control architecture. For all 5 nodes to cooperate, especially under failure conditions, they need an infallible brain. The specification defines a 3-tier control structure for this.
And this 3-tier structure ensures maximum separation of responsibility based on criticality. It's standard aviation methodology, a perfect application of top-down design.
So at Tier 1, we have the pilot's input, the demand.
That's the FCC, the flight control computer. It's the air traffic controller for the whole aircraft. It issues the overall single unified thrust command to the propulsion system. It handles pitch, roll, yaw, and just says, I need 10,000 newtons of thrust right now.
The FCC doesn't care how that thrust is generated. The real smarts, the decision-making, that falls to Tier 2.
Tier 2 is the HPCU, the Hybrid Propulsion Control Unit. This is the Grand Central Station, the central intelligence. The HPCU executes the highly complex energy management strategy.
It's the arbiter.
It's the arbiter. It decides the K0 clutch status, controls the ICE throttle, and calculates the precise instantaneous torque split between P1 and P3 to meet the FCC's demand. This is where that MECE principle is applied to energy flow. You have to exhaustively cover every possible combination of power flow.
Without them interfering.
Exactly.
And finally, the Tier 3 controllers receive those commands and execute them physically.
Correct. Tier 3 consists of the execution controllers, the EEC for the engine, the MCU for the motors, and the BMS for the battery. These are the closed-loop controllers that take the HPCU's high-level decision, like P3, deliver 500 Newton meters now, and execute it instantly.
The ultimate value here is flexibility, which is defined by the 4 core operating modes. Let's review these because they really show the optimization for different flight phases.
Flexibility is survival in commercial air mobility. So Mode A is E-stealth or pure electric.
KO, open, engine off.
K0 is open, ICE is off. Power flows only from the battery to the P3 motor. This is used exclusively for quiet vertical takeoff and landing in urban areas. Noise abatement is paramount.
Right. And if the mission requires flight beyond that short battery limit, or if the battery is depleted, the system switches to use the generator.
That brings us to Mode B series range. The K0 clutch stays open, maintaining physical isolation. The ICE runs at its optimal, most fuel-efficient RPM to drive the P1 generator.
And P1 just feeds the bus.
It feeds the HVDC bus, which then powers the P3 motor. This mode is the range extender, ideal for long-duration hovering or low-speed cruising.
But the specification highlights that Mode B suffers from inherent efficiency losses. Why is that?
It's the double energy conversion. You're going chemical energy in the fuel to mechanical rotation in the ICE, then mechanical to electrical in the P1, then electrical back to mechanical in the P3.
And you lose a bit at every step.
You do. Each conversion introduces losses. Even with highly efficient components, Mode B typically peaks around 85 to 88% system efficiency. It's a necessary trade-off for range.
Okay, so to achieve maximum power, say, for a heavy takeoff, the HPCU has to demand a different strategy.
That is Mode C, parallel boost. Here, the K0 clutch is commanded closed. Both the ICE and the P3 motor operate simultaneously, mechanically summing their torque at the propeller shaft.
All hands on deck.
It provides the highest possible power output for critical phases: MTOW takeoff, emergency climb, traffic avoidance. And critically, the P3 motor serves a massive stability role here. It compensates for the ICE's dynamic lag. Combustion engines are slow to spool up. The P3 motor, being electric, delivers full torque instantly, filling that torque gap and preventing a temporary sag in thrust.
And finally, the efficiency king for extended travel. This is what justifies all the mechanical complexity.
Mode D, direct drive or mechanical cruise. K0 is closed. The ICE is the dominant power source, driving the propeller directly. P3 might be idle, or maybe trickle charging the battery.
But the key is no major electrical conversion for thrust.
Exactly. This mode bypasses all those electrical conversion stages. The specification highlights that mechanical transmission efficiency can reach up to 98% in this mode.
Wow.
That 10 to 13% efficiency gain over Mode B is why the P13 can achieve commercially viable 400-kilometer range figures.
The ability to transition between these modes must be flawless, especially when dealing with critical safety functions. The spec quantifies the precision needed for two functions, FO1 and FO2. Let's detail these time constraints.
When you are flying an aircraft, the system has to operate faster than human reaction time, often faster than the aircraft's own natural response time.
So FO1.
FO1 is bumpless transfer. This governs the seamless handoff of torque during K0 clutch engagement or disengagement. If the timing is off by a fraction, you get a violent mechanical shock.
And a flight disturbance.
Major one.
So how fast must the system react?
The requirement is that the P3 motor torque must adjust precisely to compensate for the mechanical system's inertia in less than 50 milliseconds.
50 milliseconds. That's faster than the human eye can register.
It is. And the consequence must be imperceptible. Total thrust fluctuation must be held to less than 5% of the demanded thrust. Any more, and the flight control system sees an uncommanded input, which could lead to instability.
And FO2 deals with the inevitable failures within the components themselves.
FO2 is fault reconfiguration. This demands autonomous diagnosis, isolation, and rerouting. The goal is always continued safe flight and landing. So if the P1 motor fails, the system must instantly isolate it and switch to the next safest mode, pure electric or direct mechanical drive.
And if the main P3 motor fails?
The system must immediately force the K0 clutch closed, letting the ICE take over propulsion mechanically. And the ultimate safety ceiling here is that the catastrophic failure probability of this reconfiguration logic, the brain making the switch, must itself be less than 10 to the minus 9 per flight hour.
The fail-safe logic has to be inherently safer than the system it's protecting.
That's it.
That level of complexity, 5 nodes, 4 modes, 50 millisecond response times, and a 10 to the minus 9 target, you can't achieve that by just coding until it works.
No.
This is where you reject ad hoc development and adopt the aerospace-grade process, specifically the V model defined by SAE ARP 4754A.
It is the absolute law-governing system engineering for safety-critical aircraft. The V model is foundational. It's not just a workflow chart. It's a commitment to proving that every single element of the final product traces back to a high-level safety objective. It's how we do system engineering development.
Okay, let's follow that top-down decomposition, the left side of the V, where you translate business goals into lines of code.
It starts at the broadest definition, Aircraft-level requirements. These are the commercial and regulatory demands. A 300-kilometer range, specific noise limits, EASA certification requirements,
And you cascade down.
to the P13 system level. Here we define specific power envelopes, redundancy architectures like dual inverters for the P3, and mandated failure modes.
Like surviving a generator failure.
Right. Then we drill further down into the hardware specifics at the subsystem level. Here we define concrete, quantifiable metrics.
So things like motor efficiency must be over 95%, or battery capacity is exactly 150 kilowatt hours.
Exactly. And the K0 clutch must have a guaranteed minimum cycle life of 50,000 actuations. Hard numbers.
And finally, those break down into the lowest level of engineering direction.
These are the software and hardware requirements. This is where we define the mathematical specifics, the exact control algorithms, the processor architecture for the HPCU, maximum memory limits, the VHDL or Verilog logic for the hardware. Every single high-level requirement must decompose into multiple specific requirements at this lowest tier.
So once that decomposition is done, the left side of the V is complete. You hit the bottom of the V for implementation. But the real genius and the major cost driver is the right side, verification and integration.
The right side is the relentless pursuit of proof. It starts with proving the smallest elements work. Unit tests for individual code modules and circuit boards. Then you prove the interfaces work, software-hardware integration tests.
And then you move to the big rigs.
Then we test the integrated system in high-fidelity test beds, the Copperbird and Ironbird, for system integration tests, where the entire propulsion train is operated under simulated flight loads.
What binds this whole process together, and what ES inspectors spend months auditing, is the principle of complete two-way traceability.
It is the non-negotiable principle of aviation engineering. It means that every single high-level safety requirement, like loss of thrust being less than 10 to the minus 9, must be linked directly down to a specific line of code in the HPCU.
So every line of code has to point back to a safety rule.
Every line of code, every design feature, every test case. We use tools like doors to manage millions of these links. If we find an issue in a test case on the right side, we must instantly trace it back up to the affected requirement on the left side, proving nothing was missed. This documentation is the safety proof.
The rigor of this process is directly proportional to how bad a failure could be. This is why the Functional Development Assurance Level, or FDAL, is so critical. How is this defined for the P13, let's say, for thrust control?
Okay, so we classify the severity based on a functional hazard assessment, or FHA. So the function of thrust control is the most critical. If the system has an uncommanded change in thrust, a sudden surge, or a drop to zero,
It's game over.
it results in immediate loss of control and loss of the aircraft. Its failure consequence is defined as catastrophic.
And catastrophic failure immediately dictates the highest possible development rigor.
Precisely. Therefore, the thrust control function is allocated FDALA. This mandates the most stringent requirements for software assurance, DO178C-DALA, and complex electronic hardware assurance, DO254-DALA.
Now contrast that with something less critical, like the health monitoring system.
The health monitoring function gives the pilot status updates, temperatures, voltages, fuel rates. If the health monitor fails and reports bad data, the aircraft doesn't fall out of the sky.
Right.
The consequence is classified as major. It might cause a diversion, maybe an uncomfortable flight, but not catastrophic loss. This function is typically assigned FDLC, which requires a less intense but still rigorously defined assurance process.
And the cost difference between DALA and DLC is massive.
Oh, it's an order of magnitude.
The entire system development is anchored by the System Safety Assessment process, guided by ARP 4761. You have to prove mathematically that you hit that 10 to the minus 9 target.
The SSA process is the quantitative proof. We use powerful techniques like fault tree analysis, or FTA, which graphically breaks down how a catastrophic failure could occur. And the end goal is proving those two critical safety goals, SGO1 and SGO2, are met.
SGO1, the ultimate proof of propulsion reliability.
SGO1 is the probability of a total loss of thrust from both primary sources, the ICE mechanical path and the P3 electric path. The probability must be less than 1 times 10 to the minus 9 per flight hour.
And this is where the hybrid architecture really wins.
It does. By having two fundamentally different energy sources, fuel and battery feeding two different paths, you dramatically reduce the likelihood that a single fault can take down both.
That makes sense. An electrical short might kill the battery, but the ICE can still run.
Or a fuel contamination issue might stop the ICE, but the battery can still power P3. It makes the probability of A and B failing at the same time exponentially smaller.
And the second safety goal, SGO2, addresses a failure that is less intuitive but just as catastrophic.
SGO2, the probability of uncommanded reverse thrust.
Right.
A sudden, unwanted reversal of propeller pitch or motor torque, say from a software glitch, can instantly impose loads that exceed the airframe's structural limits.
Leading to immediate breakup.
Yes. So that probability must also be proven to be less than 10 to the -9 per flight hour. And achieving these goals requires total dedication to the process defined in the next section, certifying the software and the hardware that executes the logic.
Okay, so we've established the rigorous process and the safety goal. Now we get to where the rubber meets the road. How do you actually build the brain and the muscles to meet that extreme DALA rigor?
This is where aerospace specifications impose requirements far, far beyond any other industry. We have to ensure the control software, DO-178C, and the complex electronic hardware, DO-254, are functionally infallible.
Let's start with the software side, the HPCU control logic governed by DO-178C Level A. You mentioned the methodology itself is mandated.
Yes. For DLA functions, we must use model-based design, or MBD. We don't write C code from scratch. We design the control logic graphically in tools like MATLAB Simulink.
Why?
Because this graphical model is mathematically verifiable, and we use certified tools for automated code generation. This systematic process significantly reduces the risk of human error from manual coding. A tiny bug could cost $1 billion program.
But the real technical Everest is the testing requirement for DALA. It requires achieving 100% MCDC. That sounds like jargon soup, but it's fundamental to proving the code's safety.
MCDC, Modified Condition Decision Coverage, is truly the gold standard of software testing. Standard testing might just make sure every line of code is run. MCDC goes much, much deeper.
So break it down.
Okay, imagine you have a logic gate. If condition A is true and key condition B is true, then do something. Simple coverage tests the whole statement as true and false. MCDC demands you prove that each individual condition, A and B, independently affects the outcome.
So you have to prove that if condition A is true, but B suddenly flips to false, the logic immediately changes its decision, and it was B that caused it.
Precisely. You have to devise test cases that prove each condition is a specific trigger. This forces engineers to test every single logical permutation and dependency. It ensures there are no hidden, untestable paths or unintended consequences in the HPCU's decision-making.
And to ensure the system is predictable, there are strict coding constraints. This goes back to deterministic operation.
Absolutely. Time is the most critical resource in a real-time control system. To guarantee predictable execution time, meaning the control loop executes in the exact same time interval every single time, we strictly forbid recursion and dynamic memory allocation.
Why that?
Recursion can lead to unpredictable stack depth, maybe even infinite loops. Dynamic memory allocation can introduce non-deterministic delays. In a system relying on a sub-50 millisecond torque response, that kind of timing unpredictability is completely unacceptable.
You have to prove the execution time is fixed.
And known. And as the HPCU moves to powerful modern processors, we run into the multi-core challenge.
Right. How do you certify something where different processes are competing for resources?
This is a major regulatory concern addressed by EASA's AMC 20-193. If the HPCU uses a multi-core processor, the developers must perform detailed interference analysis.
Proving what exactly?
Proving that the execution of a non-critical function, say the DLC data logging on Core 2, does not interfere with or delay the critical DALFA, a thrust control logic running on Core 1, especially when both are fighting for shared resources like the memory bus. You have to prove spatial and temporal isolation.
Okay, moving now to the physical layer. How do we handle hardware design assurance for things like the inverters and the battery management system controller under DO-254 Level A?
On the hardware side, the verification is rigorous, but the truly unique challenges for eVTOL arise from the operational environment, specifically altitude.
You're referring to the risk of cosmic radiation.
Exactly. At cruising altitudes, say 25,000 feet, the density of high-energy cosmic rays is significantly higher. These particles can strike a silicon chip and lead to a single-event upset, or SEU,
which is a random bit flip.
A random instantaneous bit flip in a memory cell or register. If that bit controls a contactor or a motor phase, it can cause catastrophic failure in microseconds.
So you're saying a random particle from space can take down the plane?
It could, which is why hardware design for DAA demands robust SEU protection. For critical data, we use error detection and correction, or ECC memory. But for the most critical logic pathways, we often implement triple modular redundancy,
TMR.
TMR. You run 3 identical logic circuits in parallel, they all do the same calculation, and a voter circuit compares the 3 outputs. If one output flips due to an SEU, the voter ignores it because the other 2, the majority, agree.
So SEU protection addresses radiation. The next challenge is electrical integrity for that 800V system in the low-pressure atmosphere.
This is a core physical constraint driven by Paschen's law. It describes how voltage breaks down air insulation. The law dictates that air's dielectric strength, its ability to resist arcsing, decreases significantly as pressure drops.
So the risk of an electrical arc is much higher at 25,000 feet than on the tarmac.
Significantly higher. The air molecules are just too far apart to effectively stop the current flow.
So what's the solution?
The specification requires that electrical clearance and creepage distances, the air gaps and surface paths between high-voltage components, must be physically increased by at least 3 times compared to ground-level standards.
3 times. That has a huge impact on size and weight.
A massive impact, but it is absolutely non-negotiable for safety.
Okay, we've established the extreme processes and safety targets. Let's ground this in the specific, hard numbers and standards governing the hardware, starting with the 800V electrical architecture. Why the move from a conventional 400V system to 800V?
The move to the 800V DC bus is purely a necessity driven by weight savings and efficiency. We know that power equals voltage times current.
P equals V times I.
Exactly. So to get the hundreds of kilowatts needed for VTOL, if you double the system voltage from 400V to 800V, you have the required current to achieve the same power.
And having the current has a direct cascading effect on the physical aircraft.
It does. Power loss is proportional to the square of the current. Having the current drastically reduces resistive losses, which boosts efficiency, but more importantly, it allows for significantly smaller, lighter cables and wire harnesses.
And in aircraft design, weight is the ultimate enemy.
It is. Reducing wire harness weight by potentially hundreds of pounds is a non-negotiable design driver.
But 800V, with that high-speed switching you mentioned, introduces severe electromagnetic challenges. How is NEMC managed?
The inverters use silicon carbide, or SiC, because it switches electricity extremely fast, often over 40 kilohertz. But this generates intense broad-spectrum electromagnetic interference or electrical noise.
And if that noise leaks out, it can corrupt flight control signals, GPS.
All your avionics. To counter this, the spec mandates that all high-voltage harnesses use a 360-degree braided shield design. This continuous metal shielding acts as a meticulous Faraday cage around the power conductors containing the noise.
Moving to high-voltage safety, the physical guardrails, the spec mandates the high-voltage interlock loop, or HVIL.
The HVIL is a mandatory low-voltage hardware circuit that snakes through every single high-voltage connector. Its sole purpose is continuous mechanical monitoring. If a high-voltage connector loosens even slightly, the low-voltage HVIL circuit opens instantly,
Triggering a safety shutdown. And the response time for that shutdown is quantified to a life-saving precision.
Absolutely. It has to be instantaneous. If the HVIL is interrupted, the battery management system must get the signal and cut the main contactor in less than 10 milliseconds.
Same down.
Then the system must immediately start safely discharging the residual charge on the HVDC bus. That voltage must drop below a safe 60V in less than 5 seconds. This is critical for protecting crews and first responders.
Now, the battery system itself. It introduces probably the single greatest existential safety concern for electric flight: thermal management, guided by DO-311A.
And DO-311A is centered on containment because statistically a cell failure is inevitable over the life of the fleet. The core safety requirement is thermal runaway containment.
So you have to prove, through physical testing, that one cell failing won't cause a chain reaction.
Exactly. The design must prove that the high-temperature gas and heat from a single cell failure will not propagate to adjacent cells.
How do they physically achieve this? It sounds like a massive structural challenge.
It is. The battery pack needs sophisticated thermal barriers, often mica or composite sheets between cells, and a specialized dedicated venting system designed to safely route those highly flammable gases outboard and away from the aircraft.
Okay, let's shift back to the mechanical side. The coupling between the ICE and the P1 generator. You stressed the importance of torque damping earlier.
Yes, the spec makes a torsional damper mandatory at that P1 ICE interface. The combustion process is inherently violent. The damper is designed to absorb and smooth out those high-frequency torque pulses before they reach the sensitive drivetrain.
Another small component that prevents a huge failure.
It's a passive mechanical element that ensures the lifespan of the active electric components. Without it, the system would fail from vibration fatigue far too soon.
Finally, the design assurance philosophy extends to component selection. You're not inventing everything from scratch. You're selecting components with a high technology readiness level and existing aviation certification foundations.
Absolutely. The approach is to de-risk the project by selecting components built with aerospace principles in mind.
So for the motors,
For the motors, a benchmark like the Safran Engine US series is chosen because it has features like independent dual winding redundancy. So the motor itself has two electrically isolated pathways for power. If one fails, the other can still function.
safety baked into the hardware
Yeah.
and for the inverters.
For inverters, we seek combinations like silicon mobility OLA FPCUs with Wolfspeed CLR modules. The CCA gives us the millisecond level torque response we need. The OLA platform provides a foundational automotive safety certification, ASIL-D, which, while not DLA, gives a robust baseline for the DO-170TC process.
And the connectors have to handle Passion's Law and EMI.
Right, so you use highly ruggedized aerospace standards like Amphenol's HV38999 Raptor series. These are specifically verified for partial discharge-free operation at high altitude. Component selection is always driven by certification requirements.
We've designed the P13 by the book. Now comes the moment of truth, proving that the integrated system works flawlessly and meets that 10 to the -9 safety target. This is the entire right side of the V model.
This verification phase is the costliest, most time-consuming part, but it is non-negotiable. It's a progressive path designed to catch errors early. We use 3 progressive ground integration test platforms.
Let's start with the brain validation, HIL testing.
HIL, or hardware in the loop testing. This is step 1. The actual flight-ready HPCU hardware, the controller brain, is connected to a powerful, real-time computer simulation of the entire aircraft.
So it's basically a flight simulator for the control unit.
Exactly. It lets us test the software against a highly realistic dynamic environment. And the most critical activity here is fault injection.
Ah, so you try to break it.
We introduce catastrophic scenarios without destroying physical hardware. We inject simulated sensor failures, communication loss, even a contact or welding shut. Then we rigorously test the system's ability to autonomously diagnose the fault, isolate it, and switch to the next safest mode, all in real time.
Once the control logic is proven in simulation, you move to testing the pure electrical systems.
That's the copper bird test. This is the full-scale electrical test rig. We integrate the actual high-voltage hardware, batteries, inverters, the HPCU, the full 800V harnesses. The focus is highly specialized, verifying 800V power quality, confirming EMI characteristics, and ensuring the rapid response of the HVAL safety mechanisms.
So Copperbird is just the electricals, no moving parts.
Right. We use dummy loads to simulate the motors. We're verifying the integrity of the electrical power transfer itself before adding mechanical complexity.
And finally, the ultimate ground test platform where everything comes together.
The Ironbird test. This is the full mechatronic test rig. It integrates the real thermal engine, the P1, P3 motors, the K0 clutch, and the propeller shaft, all connected to massive mechanical loading systems that simulate the drag and torque of flight.
And the core purpose here.
Verifying the entire mode switching logic under real physical stress. We check the torque smoothness during K0 clutch engagement verifying FO1 in the real world, and test the automated failure reconfiguration while the system is physically generating thrusts. This is the last stop before flight testing.
The project's success is ultimately measured against quantifiable metrics. The acceptance criteria, the red lines. What are the crucial performance metrics that must be hit?
Efficiency and agility. Since the hybrid justifies its complexity through range, the total system efficiency in cruise mode must be proven to be greater than 92%.
If it falls below that, the whole commercial model is in question.
It is, and we must prove the agility of the mode switching. That stringent safety limit translates into a performance metric. Thrust fluctuation during any transition must be less than 5%, and the disturbance must last less than 200 milliseconds total.
With the core torque adjustment hitting that 50 meters requirement.
Yes, those are the hard numbers that define a stable, airworthy transition.
Safety validation, of course, relies on passing the component level standards.
Precisely. The battery systems must pass the DO311A thermal runaway test with no external fire or explosion. The HVIL cutoff must be proven to be less than 10 milliseconds. These are binary pass-fail criteria.
And the final dimension of acceptance criteria is about the quality of the V-model process itself.
That is process verification. All the vast documentation must be finalized and approved. Specifically, the DALA software and hardware must achieve SOI 4, Stage and Involvement 4. This is the final approval milestone from the certifying authority, confirming that the process used was robust enough to justify the 10 to the -9 claim.
So all this work leads to the final type certificate.
Mm.
What's the fundamental regulatory foundation this is all built on?
The path is clear. For Europe, it's the ESA standard, SC VTOL 01 Issue 2 Category Enhanced, and the hybrid propulsion system specifically follows the special condition, SCE 19.
And the core principle.
The core compliance method that underpins all this development is continued safe flight and landing, or CSFL capability after any single point of failure. The loss of the ICE, a battery pack, or the P3 motor must never lead to immediate loss of control. The remaining system must be capable of bringing the aircraft safely to ground. So if we synthesize everything we've discussed, the core conclusion is definitive. The strategic success of the P13 architecture isn't derived from the peak performance of any single motor or engine.
It's not about the parts.
It's about the completeness of its system integration and the flawless, documented execution of the entire aerospace safety framework, ARP 4754A, DO178C, and DO254. It is an architecture defined and proven by its rigorous safety process.
It's truly fascinating. The constraints of physics, the battery wall forced engineers to embrace hybrid complexity, but the non-negotiable demands of aviation safety meant they couldn't just adapt to automotive standards. They had to invent a hyper-reliable system to meet that near-impossible 10 to the -9 target.
And this transition from pure electric back to highly optimized hybrid systems is a necessary bridge for AM to achieve true commercial scale and regional range.
So what's the next battleground for certification?
It isn't the physical hardware, which we have processes for. It's the robust V&V, the verification and validation of the Intelligent Energy Management Strategy, the EMS, within the HPCU.
Meaning they built the parts. Now they have to prove the brain can use them perfectly under extreme stress.
Exactly. Engineers must rigorously demonstrate, especially through those intense fault injection scenarios on the HIL and Ironbird rigs, that the control logic will always choose the safest, most efficient, and most stable reconfiguration path. Proving an algorithm can reliably manage a sticky clutch, a venting battery, and a failed generator simultaneously, while maintaining a 5% thrust margin. That is the ultimate challenge.
So what does this all mean for you? Consider how the lessons learned from integrating a high-voltage, high-altitude hybrid system governed by principles like 100% MCDC test coverage and Passion's law compliance might influence other industries. Think about high-speed rail, massive autonomous construction equipment, or even next-gen data centers that need both high-density energy and absolute reliability. The complexity of certifying this system to DLA standards is a blueprint for reliability far beyond aerospace.
And that is where we land today on the state of hybrid propulsion engineering.
Thank you for joining us on this deep dive.